Welcome back, everybody, to the second day of our AI summer. You'll recall that this week is going to be a little bit different. We're only going to be meeting, we met Monday, we're going to meet Wednesday. We're not going to be meeting Friday because Friday is Vanderbilt's commencement. And I don't know about you all, but I'm going to get dressed up all funny, and I'm going to be a marshal for graduation. So I'll be busy doing that, and we'll be picking this up next week, where we'll return to our Monday, Wednesday, Friday. We'll deviate from that again for Memorial Day, closer to the end of the month. Before I start asking you questions about some of the things we covered on Monday, what questions do you have for me about anything that we've talked about before, or anything about AI models? All right, then let me go ahead and let me ask her permission to enter into a contract with you. I would like to help ensure that that everyone has a chance to participate, and frankly that everyone sort of gets into the practice of participating as well. So what I'd like to do is I would like your permission to call on you, even if you don't raise your hand, to call on you with questions. But the caveat is, at any point, if you're not ready to answer, if you're just, you're feeling shy or you're just not into it, you can say, I'd like to pass. No harm, no foul. We'll expect that. So if you're called and I was like, I'm still trying to figure this out, feel free to that you're going to say that you're going to pass. Give me a thumbs up if that sounds good. So you can get to your you can get to your reactions, and you can give me a thumbs up if that is okay. Fantastic. Okay, great. Looks like we have good general agreement. Got the thumbs up. All right, excellent. Fantastic. Then let's go and get started. I'd like to ask you some questions about what we covered last time. So here you're taking a look at a graph. This, my graph, how I kind of think about how we've talked about AI over the decades, and something changed really pretty drastically between the 1950s and all the decades after that, when we talked about AI, and then we didn't want to talk about AI anymore because it didn't really match up to the promise that we had for it. What are some things that have changed since 2010? What are some things to change such that when we talk about AI, we actually talk about something that that people across the world are using to actually solve problems? What's changed?
Computing power?
Yeah, okay, that is one that I didn't actually have in there, right? Computing power, you're absolutely right. To be fair, we did have really, decent computing power even in 2010. So that got us convolutional neural nets, and that got us good vision models that actually worked. Some other things, though, changed as well. That's a good call out. What are some other things that have changed about how we think about and how we work with these models, and how we come up with these models?
I'm not sure how helpful this is, but I'm remembering this visualization of sort of a tree and ours, they were doing forest tree regression, and somehow, we've sort of gone up the scale on that to where we are now, which I'm assuming is just an improvement in the algorithm, and the learning has continued. Not super helpful.
No, actually, but so you got a couple of really important things. So let me expand on those. Thank you very much. So one was, you mentioned machine learning and then something else. Tell me a little bit about machine learning. With machine learning as we define here, these are a little bit fuzzy terms, but when I say machine learning, I mean statistical learning, machine learning, like random forest, logistic regression, gradient boosting, these sort of techniques that we've had around for a little while. Can you directly use unstructured data with machine learning?
No.
Yeah, no, great. And Tara, thank you for answering. Anyone can answer, but Tara, thank you for stepping forward. So no, right? So you have to have that all prepared, right? So that's one thing which is different, because with deep learning, we don't have to have structured data. That's a big difference. When you have trained a model in using these machine learning techniques, how many problems have you solved? In other words, you defined a problem, you came up with a solution for it. Have you solved lots of other problems?
No, you've created more problems.
Right? You could say you've created more, that's right. But certainly the problem is that solution is really only good for that
Yep.
one thing. Remember, we talked about customer churn, sort of a traditional business use of this, and you could predict customer churn. Tremendously useful. It has value. I mean, this is worth, this has been worth billions of dollars. This has really moved research forward, but you solve one problem. You solve one problem, you solved one problem. That's it. So those are sort of the characteristics of machine learning. Tell me what's different about deep learning. First of all, can you work with unstructured data? For example, could I just put an image up and do something with it? Or can I just put text in to a deep learning problem like an AI model? Can I do that now?
I believe that we said with a deep learning, yes, unstructured data became more useful.
Exactly, that's right. You do this all the time now, right? You type in what you want. You didn't structure that. You didn't say, here's the noun in my sentence, here's the object, here's the, no, you just you ask it, you type it, you take pictures of things, and you ask for information about it, you talk to it, completely unstructured. So these models have the ability to deal with unstructured data. So that's one big difference. The other thing is when we train an AI model, is that model good for only one task, or is it good for many tasks?
Many now. So it's a generalizability, right? Is that?
Generalizability. So a couple of things, that's transfer learning, right? So that's one of the big keys, transfer learning. We train a model on language broadly defined, and then it can solve all language problems. So that's transfer learning. Two, we now have a way of training these models that doesn't require supervised learning, right? We don't have to prepare all the data so we have all of this structured data and then outcome. Now we can give it text. How do we train it with text? What's the task that we do? Remember, we did this with that first sentence from Their Eyes Were Watching God, Zora Neale Hurston. Remember what we did with that? What was our task for ships on the horizon? What was our task?
All of us input basically the first thing we thought of when we read the line, the first solution we thought of.
That last word, right? So that's the task that we train generative AI models on, is fill in the missing part. And in particular, fill in the missing last word. So that's a new type of training. So that's called self-supervised training, right? So two big things that have changed. One, now we have transfer learning. Deep learning models give us transfer learning. Train on one thing, train in one way, many different uses. Two, now we have a better way of training the models so that we don't have to label everything. We don't have to use just supervised learning. So rather than painstakingly creating this training material, hey, you got some text? Great. I can train on that. Can somebody help me out? And here I'm going to call my first person. Let's say that what I want to do is that I want to train a model on an image. So can somebody help me out here? What might I do if I know how to train a model on text, right? I leave out some of the words, or I leave out the last word. Ethan, and remember you can pass, so help me out here. And you can even practice passing so other people can see how to do it. But Ethan, how would you train a model on images in this self-supervised way?
Yeah, you can leave out a pixel value for the color and then go from there.
That's it. That's it. Yep, you leave stuff out. Turns out you have to leave out like a big chunk. There's a lot of redundant information in images. So you're leaving out like up to, it can be like 40% of the image gets blocked out. And it could be by, and there have been studies on like, it should be a regular pattern, should be random. Random works best, but random blobs that you remove out of and you say, fill in the missing part. Exactly. That is one way to train. Let's say that we wanted to train, okay, we'll leave it right there. So fantastic. So that's another big thing that's changed. Let's see what else has changed here. So, and Tara, you talked about this. You said algorithm. So that's the other important thing here, right? Is now we have a general purpose, powerful learner. And this is the transformer. And in particular, the part of that seemed to be the secret sauce was attention in the transformer. So now we have a general purpose learner. We have a good way to train it that doesn't require us to pre-prepare data. And when we have those two things, we have transfer learning, which means after we do that, now we can use that in myriad of other ways. Fantastic. All right, let me go and flip forward here a little bit and let me ask you about this. So here we have transformers of different types. And let me spell this out a little bit more. So this is called a decoder only transformer over here. BERT, very important model, and other models like that over here on the left. In the green, in the middle, is this is called an encoder decoder model. These are a little bit less known. And then here we have the ones that have made all the difference in the world. These are decoder only models. So I'm going to talk about what that means. This was the original transformer model that was proposed. This is an encoder decoder model. This is exactly what it looked like in that early paper. Attention is all that you need. And the model has a couple of different parts. The first model was trained to do translation. This is called sequence to sequence mapping. So you put in one language and then you get out another language. And it was kind of complex. It had two parts, right? It had this encoder, and we've talked about sort of what this looks like, the tokens and the embeddings and this encoder stack. And we'll talk more about those in a moment. But it had another part as well, which was the decoder stack. And these two were connected in some way. We'll talk about this just a little bit. We're not going to get too much into this. You're welcome to take my class if you're on Vanderbilt campus, if you'd like to get more in depth. But this is what's called cross attention here. So this was the full model, and this is what we see right here. This is the encoder decoder model. This is that whole original model, right? So when we say that in that green, this is that whole model. But here's an interesting thing. What we discovered was you don't need that whole model. You could take only the encoder part. So this is only the encoder part. So that is just this part. Turns out that was dead useful all by itself. Over here is the decoder part only. It turns out the decoder part, come on, there we go. The decoder part, just this part, was also tremendously useful. As a matter of fact, this one we found out scaled and could do remarkable things. So this part of the model, its job is to produce useful representations, and then you do something with those. So this could be, you could do classification, you could do sequence beginning end prediction, but you tend to use this raw output in some way. The decoder part actually takes some sequence and then makes a prediction about the next token. That's what this decoder does. And this is what GPT does. This is what GPT-4, ChatGPT 3.5, all of those are decoder models. So here are all the decoder models. And what we found out was that decoder models, they didn't have to be purpose-built for things. Once they learned language, you could do a lot with this idea of something to predict just the next token. So here we have GPT-3 right here. So here's GPT-3. On the lower part, let's see, can I point to it? GPT-3 is, I'm doing this on my iPad, so I can't point directly. But if you go to the gray part and you look at GPT-3, oh, I can do annotations here. Let me set up and do my annotations. Oh, heavens. I did not set up my annotations. I'll have to do that during a break. So we have GPT-3, and then we sort of go past 2021, and then we go up here. Can somebody tell me, between GPT-3 and Codex, right? Between GPT-3 and Codex, what changed? I mentioned this just briefly. Yes. Mohsin.
I think you said the reinforcement learning with human feedback.
That's right. The model itself didn't change, right? We didn't change the architecture. The model still kind of looked like this. That architecture didn't change. What changed was how we trained it. So in GPT-3, we just gave it the raw training. In Codex, what we did, we gave it special training on code. So not just general text, but now we started to train it on different programming challenges. And so we gave it part of a program, and then we had it guess the last token in coding challenges. Instruct GPT, Mohsin, you anticipated this a bit. This is where we train the model on how to be a good chat partner. And that was the reinforcement learning from human feedback. So same architecture, same base training between Codex, InstructGPT, and ChatGPT. All that's changed is what we trained it on. So same architecture, different training on what we were training it on. Okay, fantastic. Questions about the tree or about anything that we've talked about so far? Tara.
So what has happened between where we were early in the year to Databricks? Huge leap.
It's a great question. So let's, and actually, I'm going to be talking through that in just a moment, but let me do that in context in just a few minutes. But would you remind me if I don't answer your question? I believe we're gonna get to your question. Here's a hint. So the model in the decoder stack that you see here in the middle, right? That's all the knowledge of the model. And we're going to see in just a little bit, this has, in that decoder stack, it has attention and feed forward. Feed forward is where the knowledge of the model is. So think about this. If you wanted a model to get better, if you wanted a model to know more, ask yourself, what part of the model would you grow? What part of the model could you make larger so that it would know more? So think about that, and then we're going to get to the answer in just a few minutes. John.
So kind of looking at the evolutionary tree, it's pretty startling to see, all the different branches and all the different like explosive progress that's been made in a 5-year span.
Yes.
I think I'm correct in saying that these models have been pretty iterative. Is there something sort of among the 2023 bracket, like Claude or GPT-4? Obviously, we can't predict anything, but is there a feature or advancement that's projected to sort of branch further out? I guess what I'm asking is, are we going to see, speaking in terms of the graph, are we going to see faster up or faster out?
So I think that really this tree is going to need a sort of a strong branching off, because this does not include multimodal models, and that's going to be extremely important. And the other thing that you won't be able to capture with this is a different use of these models, which is agents. You're going to start seeing agents. We're going to be talking about those as well. But right now, we're using these models directly, raw. If I want to do something, I talk to GPT-4 itself. when what I could be talking to is multiple GPT-4s. Here's a problem that I want to have solved. Now, there could be a GPT-4, just one instance of it, that's responsible for tracking how well the solution is coming along. But another model running right beside it, no different architecture, but just running right beside it, could be the doer, writing programs and testing it. So this GPT-4 could call this other model and say, okay, we need to solve this problem, write this code. And then the GPT-4 says, this doesn't work as well. We can get a little bit close to that by asking a single question. But think about how much more you can do if you ask a team to do something versus you're asking a person to do something. I don't know if you've ever been in this situation where someone says, hey, I want you to do something for me. So, I'd like for you to solve this problem, and then I want you to assess it to see how well it's going. And also at the same time, I'd like for you to go ahead and prepare, materials around this as well. Oh, and by the way, keep track of, and you're just like, your head's exploding, right? Well, imagine that you have multiple agents that communicate directly with one another because GPT-4 knows how to chat. GPT-4 can chat with another version of itself. These are called agents. So that's going to be another big advancement. Don.
So clearly the decoder-only tree has been prolific and obviously explosion and so much excitement about it. But I'm struck by the green encoder-decoder tree continuing on, and Google obviously putting a lot of effort there. Is there something that's doing particularly well that they're chasing?
Yeah. So think about the following. In order for GPT-4 to be as dead useful as it is and be able to do all sorts of different tasks, it has to have immense world knowledge. This makes it an amazingly large model, extremely difficult to train, extremely difficult to even inference on. So you're running GPT-4, it takes a lot. There are more efficient models, but still these models are huge. BERT and even models in the middle, these are on the order of millions of parameters, maybe a few billion parameters. GPT-4 is trillion parameters. It's huge. Now, it's a jack of all trades, master of a few. But you can think of the models on the left as being master of a task. It can answer questions about this one particular thing. Don't ask it to write a poem. Don't ask it to be funny or make it rhyme. That's not going to happen. But it can do one thing with fewer parameters, faster, cheaper, better than GPT-4 if it's been trained on a particular task. So it depends on what you want it to do, and there are definite trade-offs. Michelle.
Thank you. So when you're talking about like agents who can run like simultaneously together, is that when you're using that token encoding? So like it goes into the reversibility and lossless? Like, is that how that?
It's higher. So it's like the entire GPT-4 producing text. And what it's doing is it's literally talking to the other agent. So the communication between agents is English or whatever language you choose. So it's much, so rather than being in the architect, this is way, way up here.
Oh, okay.
So you can imagine you might have a model that's been particularly fine-tuned in a particular area. You might have another model which just has a prompt, which describes what its job is, right? But they have different tasks and they're keeping track of different things. Because if you think about it, it's very difficult to hold several tasks and goals in mind at the same time. Have you ever noticed that when organizations, teams, organizations, companies, when they set goals, they only ever set like 3 or 4 goals? The smart ones. And companies that try to set like 12 goals for the year, they're like, they never get to them because they can't attend to more than about 3 or 4. A single entity, a single organization can only attend to that many. And so it's a big thing to ask for a GPT-4 or some GPT to keep track of 5 things you want it to do. It's not going to do it well. But if you have 5 different GPTs that talk, now you're cooking.
Okay. So then, sorry, one more question if I can ask that. How are you getting them, like, how is that structure then to get them to be able to communicate, to share the data?
That's a great question. And that is going to be, I think, and Churro, you can keep me honest, I think that is week 3 when we introduce agents.
Okay, great.
Absolutely.
Thank you.
Absolutely. Amir.
Yeah, I'm just going to ask a question that may sound quite naive, but so could it be the case that after a while of ChatGPT or any of these decoder models being trained by like this self-supervised training sort of thing, could it be that they reach a point where they have only enforced their own output, and so the quality of the output will drop? It won't be the representative of the current knowledge they have, but it will be biased by what they're producing?
So a couple of things here. One, when I say self-supervised, that's just sort of the name, right? Really what that means is we're leaving out parts and we know the part that we left out, and that is sort of the training. So the process is self-supervised. It doesn't need a person. You simply say, hey, take this entire book, break it up into sentences and leave out the last word and train on that, right? So self-supervised is a little bit, it's not a great name, but it's better than supervised. We want to get across, it's kind of supervised, but the entire process doesn't require you to label everything.
I
So
see.
that's what's going on there. But you bring up a point of sort of text that's generated by the models being out there on the internet and the training on that.
Yes.
We were very concerned about that early on, poisoning our training sets. But it turns out not really poison. Think of it more, it's like it's still useful, like candy bars, right? Candy bars aren't great for you. They're not poisoning you. They have calories, they have a use, but too many of them, and then it begins to degrade. Kind of a similar thing with information generated by the model, by output generated by models. It was generated by a prompt. There was a purpose behind it. People looked at it. You can use data. You can use training data that's generated by a model to train another model, and so long as that's a process that is intentional, that can actually work really well. So it's not an immediate problem, but in the long run, yeah, that's going to be something to think about. You really ought to curate your data set so you know what's going in. Then there's another problem that you didn't quite mention, but I'll put out. If you don't mind, I'll put into your I'll put in your mouth, which is, can training degrade over time? So think about us. I don't know if you've ever, heard the joke or said the joke, that, you've been cramming, you've been, studying for your qualifying exam or a final exam. And, like, if I learn one more thing, I'm gonna have to forget something, right? Right. I'm gonna forget how to tie my shoe after this qualifying exam. That actually can happen, and it's called in models, and that's called catastrophic forgetting. And the idea is that by learning, you disturb the other previous learning. It turns out there are ways to approach that, some mathematically beautiful methods to handle that. But that's an active area of research of how do you train a model and avoid catastrophic forgetting. And that's especially important as we train up these models, they get a world knowledge, and then we want to update that world knowledge, right? If we want the model to understand something more just directly in the model, and we're going to find other ways to augment models in just a moment, but it's going to be very important to train them a way that you don't disrupt their previous learning. Other questions? Great questions. Let's go ahead and jump in and talk a little bit more about the architecture. Have some questions for you. Somebody tell me, and I'm going to go and just ask, and you can pass. Remember that. Can somebody remember? Anybody remember what token encoding is? What do we mean by that? What is a token encoding? Let me start with Marcus. Marcus, do you remember what a token encoding is? And you remember, you can pass.
Hi.
Hi.
So from my understanding, a token encoding is like the basic unit of OpenAI GPT models that use to compute the length of a text. So they can be
It is-
groups of characters and sometimes aligned with words, but not always.
You were right there in the neighborhood. You're right there in the neighborhood. That's right. So it has something to do with text. It's important. Tokens is important to think about. So you're right there. Let's see who else might be able to help out and sort of to bring this this home. Harper, can you help a little bit?
So it's like so it basically translates tokens into the root words, and it also gives them weighted values based on
Can you
importance.
flip that? Reverse what you just said.
It translates
The word.
the root words into tokens.
Yes, that's it. That's token encoding. Fantastic. So deep learning models can't work with words. They can only work with numbers. Token encoding is taking a word or a subword and turning it into indices, essentially, just integers. 1, 2, 3, 4, 5, 6, 7. Let's see. Mohsin, were you going to add something else to that?
Yeah.
Yeah,
Oh.
sorry about that. No, I think you just said it. It's basically, yeah, just putting a number, an integer effectively to a word.
Right. So this is kind of interesting in that you don't get to change this after you've done this, right? Once you've decided that 42 is cat and 43 is dog, you don't get to switch in the middle. You can't say, well, I'm going to redo this. 43 is cat now. Well, no, then that switches, the model only knows the numbers. So that's why even when we had some problems that we found with GPT-3, and remember, GPT-3 was around, it still is around, right? It had that long path all the way up. Can somebody describe for me a problem that came about because of the choice of token encodings for ChatGPT, which later became ChatGPT 3.5? Ezra, do you remember what the issue was?
I don't, but I imagine it would be something along the lines of giving a higher value to an incorrect association.
So so here we're even before all that, right? Here's like all we've done is decided, hey, cat is 42. Retrieval, that's gonna be 3 different tokens. That's gonna be 7, right? So it's coming up with a numbering scheme. So you're right, that's a concern what you just mentioned, but even before then, that's a good start. Mary, would you have an idea about what some of the problems were from our choices of our tokenization scheme?
I'm going to go ahead and pass.
Thank you. Thank you for modeling that behavior. I appreciate that. Maggie, can you recall?
Sorry, I'm going to pass.
Okay, not a problem. Let me go and take some volunteers. Who can remember? And I'll give you a hint. It has to do with, okay, Shane, what do you have?
Yeah, I believe you said that the strategy of tokenization was more effective for example, in English than other languages.
That's it. So when they made the decisions early on about how to break these words apart, they did English first. So was that a good choice for Arabic? I can tell you no. So what happened with Arabic is you need a ton more tokens to represent the same concept, the same word, right? Because when you translate a word, into Arabic, now you want to represent that word with tokens because we're not even at the level of meaning yet, right? We just want to represent this as numbers. Turns out you needed a lot more numbers to represent words in Arabic, any language other than English. So it was English first, and then other languages just were not as efficiently represented. So that was a problem because now instead of learning, you might have a useful word which has a single token, but in Arabic it might be 5 different tokens. Michelle.
So with like large data sets too, like wouldn't the tokenization be like slow at processing as well?
Yeah, slow and more expensive, right? I mean, because you've seen GPT-4, and as it produces words, it's producing tokens. So imagine it needs to produce 8 tokens before it produces a single word on the screen. It's slower. It also costs more. Amir.
Yeah, I was wondering, why was the math done by the early versions? Why was it so bad and now it's not? Like what changed there? Because it was obvious, I guess numbers were tokenized too, right?
Oh, yeah. Yes, and actually numbers is a very interesting thing. So I will touch on that too. Notice when GPT-3 was first done, that's like 2020. You can do whatever you need to. It doesn't have to be perfect. This is an early version of it. Nobody's using this in 2020. This is researchers. Yeah, we want to make this useful, but let's do it on the text that we have. No one's complaining. So we're going to do that. And then we do Codex, then we do Instruct GPT, then we do Chat GPT, and oh my God, people all over the world are using this. And guess what? And if they're not using English, it can do it, but it's not great. So whoops, but you're stuck. Once you've decided on your tokenization scheme, you can't move it forward anymore. Numbers, very interesting thing. Numbers are tokenized like words. So if I say 123, when I say 123 to you, 1, 2, 3, that's 100, that's 1 in the hundreds place, 2 in the tens place, and 3 in the ones place. 123. But if I'm tokenizing, let's say that I see 12 all over the place. So I'm going to tokenize 12. The characters 1, 2. That's tokenized. That's token number 39, because I see it a lot. 3, I see 3 a lot, so that's going to be tokenized. So now I have 2 different tokens representing the number 1, 2, 3. Everything's lost. The place value is lost. It doesn't understand numbers the way we understand. So when people joke, they say, ha, 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 the models can't do math. Well, yeah, because we crippled them when we did the straight tokenization scheme for everything. Words, numbers, yeah. There are alternative tokenization schemes, but they've not been picked up as much. Turns out through brute force of learning, you can say, by the way, when you have this kind of token with this kind of a token, all these are number tokens, you need to think of this differently and associate differently. Requires a lot more work. But that's why earlier models just couldn't add very well, because, yeah, it was like they tokenized it completely differently. Excellent. Yi.
So just want to make sure. So when we do the tokenization, it can be words and also can be letters. Is that right? Or like how do they like find the typos in there?
This
like,
is. Did you say find the typos?
Yeah. So I just want to make sure the tokenization can be. Is this word based or is letter based?
Yes. Because you get to choose how you want to do your tokenization, right? You could do, there's sentence piece, there's like byte level encoding. There are all sorts of different ways you can do it. It depends on how you would like to tokenize it. The fact is, you or the designer of the model has to come up with, either come up with or choose a scheme to move from text to numbers. So if you do byte level encoding, that's cool, because then you can represent any language that you want. But the model's going to have to do more work because it has to tie everything together at the byte level, right? Sentence piece, all right, well, that's great, because now you have more letters together. That might help you learn earlier, but maybe not be, the particular scheme you may choose may not be as good in particular languages than other languages. So, but keep in mind, and this is a little hint of what's going to come, the models are powerful general purpose learners. They can learn any tokenization scheme you want. And it doesn't matter if it's words, or you're tokenizing images, or you're tokenizing sounds. It's learning the relationships between the tokens. That's what it's learning. Abby.
Yeah, so I guess I'm wondering how, or if we know how it determines which like parts of words to Like, is it done by like morpheme? Is it done by like, I'm just interested because
Yeah, no,
that
absolutely.
plays into how.
So think of this more as a statistical and optimization problem. And right. And so is there a scheme which did morphemes? Probably. Is it in common use? No. But there are many, many different approaches, right? And the funny thing is the ones that are handcrafted, like carefully thought through and handcrafted, tend not to work as well as the ones which are kind of brute force. Let's do it statistically, meaning let's do the word counts. Hey, if I give this collection of letters, its own token, then that gives me savings. Turns out that actually works better than trying to handcraft. And again, because you're appealing to the statistical regularity. Ethan.
Hi. So what's the point of associating a number with a token if the numbers that you're associating with the token don't necessarily mean anything with each other?
So the problem is, in order to not do that is, well, first of all, let's say that if you let's just say you take any number and you just make that number the token, you give it the same number. Okay. How are you going to encode 3.1415 pi? Oh, geez. Well, that's a problem. And to give single tokens to all the numbers, I mean, do you give it to the individual numbers? But even then, now you're still having to tie them together. So there are schemes. I won't really be able to get into them. They sort of dive down. But know that almost all models, with very few specialized exceptions, are encoding numbers in this way. So the learning of what numbers are and addition is and multiplication is, the learning of that is all by the model itself. It's not getting a break. It's not catching a break at all. It's doing it through brute force. But we're going to learn in just a moment, there's a workaround, which is, actually, can you all do this in your head? Just 356 times 24, real quick. No? No hands up? What are you going to do? You're going to pull out your phone calculator and you're going to say, what were those numbers again? And then you're going to look it up. Turns out that's kind of the path forward when you're trying to do things that the model itself is not great at. You call tools, and we're going to be talking about that in just a moment. Other questions? All right, then let's move on here. So here we have our model. We have token encoding. Next question, token embeddings. What do we mean by token embeddings? And let me take volunteers here because this one's a tough one. I'll give you a hint. King minus man. Right.
We use vectors.
Harper, okay, great. So vectors. Okay, great. So Amir, what were you going to add to that?
Oh, I was just gonna say it's the space relationship between the different tokens.
Yeah. When we say embedding, we mean embedding in this extremely high dimensional semantic space. Your location has meaning, right? So we're saying here's this token, cat, and it's going to be right here. This is where cat is. It's the first pass. Maybe it's in the wrong place, but the token itself has a starting place. The 50s beat poets were real hep cats. So this does not mean meow, right? So I put it here next to the litter box, but this is not where hep cats goes. That's actually like way over here in out of date, colloquialisms having to do with whether you were cool or not, right? But this is the starting point. So that is that token embedding. It's taking every token. So for every token that you have, it associates it with a vector, which is its location in this high dimensional space. And then from this point forward, everything we do is vectors. Everything is vectors. We are moving the vectors around a little bit. We're averaging the vectors together. We are enriching the vectors. So that's what's going on. And remember at the end, okay, so let's the hidden states is simply the final state of those vectors, and then we do next word prediction. I'm going to flip forward here. And we talked about, I'm not going to go back through, now we're going to explode this out a little bit. So here we have we have this token encoding. We have the token embeds. Something we didn't talk about before, it's called positional embeds, and that's just adding a little bit of information to each token to inform where it went, in which one it was. So when I said we're real hep cats, I've added a little bit. So I start with the token 42. That 42 got identified with a big vector. I'm going to add a little bit of information to that vector. I'm going to add a small number to that vector to let the model know that this was the 9th token in the context. That's where the word cat appeared in that in the context. That's the positional embedding. Like a little breadcrumb. I'm not explicitly stating where it was. I'm giving a breadcrumb about where it occurred. Was it the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 20th, 100th? You know, where was it in the context? Let's take a look at the encoder stack. We have multi-head attention, and then we have feed forward. So there are 2 ways that I mentioned just briefly last time about how to think about what's happening. And one of them is enriching a single token. So you enrich a single token, you give it more information. Another one is I mix the tokens together. One token informs another token, right? So by looking at those 50 beat poets, 50s beat poets were real hep cats. Hep is going to inform cats, and right? And poet is going to influence cats. All of which is making me realize I'm not talking about kitties, right? So this is cat. What part of this encoder block is responsible for that communication between tokens? I'm going to share the joy just a little bit. So Josh, and remember you can pass. So Josh, which of these, and so it's got to be one of this, got to be the attention or the feed forward. Which of these do you think is responsible or is responsible for the communication between the tokens, where hep influences cat?
I'm gonna go ahead and pass. I'm not sure.
That's fine. That's cool. For deep, what do you think? Is it attention or is it feed forward?
I think it's feed forward. I'm just taking a guess.
Which is fine. All right. I'm going to ask someone else, which should be a big clue. So between multi-head attention and feed forward, which is responsible for communicating between the two? Fanji?
Sorry, could I repeat the question?
Sure. Yes, absolutely. So when we talk about communication between the tokens, right?
Mm-hmm.
Communication between the tokens versus a single token being enriched.
Mm-hmm.
Which is responsible for the communication between tokens? Is it multi-head attention or is it feed forward?
Also, communication between the tokens is the responsibility of the attention part.
Yes.
And the enrichment of token is the multi-layer perceptron part of the network.
Yep, absolutely. That's right. So attention is when we actually, when we combine information across tokens. Feed forward, and as you were saying, absolutely multi-level perceptron, just like a dense net, is when we enrich each individual token. Now that I know that cat has been informed by hep and by 50s poets, now I know that really it belongs over here, which has to do more with being cool. in a decades old sense. Okay, so now it's going to be informed by all the knowledge of the network of what it meant to be cool in the 50s, right? So this cat is a person rather than a kitty. This person might wear a beret. This person might hang out in coffee shops. That's the job of the feed-forward network, to inform once things have been moved around. And you might recall this: time flies like an arrow. You can think of the other words coloring and modifying the word. So flies before is distinct. It had a single location. But now, after self-attention, it's more like soars. It gets influenced by arrow. It gets heavily influenced by arrow. And so now it takes on the meaning of soars. So flies becomes more like a verb, right? And it's more like soars. Whereas the other phrase, fruit flies like a banana, well, now it gets influenced by banana. It gets influenced by fruit. These are nouns, and so it takes on more noun-like properties and becomes it's going to be closer to insect. And you can actually map out what this looks like and what the attention weights look like. What the attention influence looks like. You can map it out when you're running these models. Okay, so let's go ahead. Any questions so far before we dive into our next section? We're going to talk more about the models.
Could I? Oh, sorry, I have to raise my hand. So so that figure you just showed, which showed the relationship between words, yeah, this one, you can actually output this, like.
Yep. Remember, everything is computable, right? So yeah, you can at any layer. It's something you have to actually have the model, right? So you can't do this with like GPT-4 because GPT-4 is closed. You don't get it. But let's say that you run Llama 3. Yeah, you can inspect it. You can see what's happening and how things are moving and how things are being influenced. Yeah.
Very cool. Yes.
Excellent. All right. So, just to reiterate, when we're talking about embeddings here, right? So what is flowing through here, and you notice the X in and the X out, those are vectors. Those are vectors that are very long. It depends on the size of your embedding space, but the size of the embedding space means how many dimensions you have. So when you have cat and you first do that token embedding, how many dimensions is it? And from that point forward, you're going to be moving that around. So you might have, like Bert had 768 dimensional embedding space. So that meant that vector was 768 numbers long. And as you got informed, it got moved around into the 768 dimensional space. It's all the meaning, all the information, all the useful stuff is tied into the embeddings. You have one embedding for each token that you have. And the trick at the end is you do an unencoding to move back into tokens. And that's what's happening. So you have the unknown final token that you want to be able to produce. It's a vector that's sort of being moved around, shoved around by everything else. And you do an unencoding. You say, which token is close to this vector? Here's the token that's closest. Here are all the vectors that are near it. I'm going to unencode it to this token. So that's what's going on. Shane.
Yeah, I think there was a good question in the chat that is I've been wondering as well, which is it's apparent that this process is used when you type something into ChatGPT and ask a question, but is it also the same process in training? Are they the same process, or are there different parts that are used for each?
Yeah. So here's the interesting thing when you're training a model, and Sophia, I see your question. Good question. I'll answer that one too. As part of training, you're always going to be doing feed forward. You got to do that part, right? And so what happens is you're doing training, and this is through back propagation. And we can go back here and sort of see what this looks like, right? So you put in ships at a distance have every man's wish on blank. You do the forward pass, that's inference, it's called forward pass, and it produces a word. It said, oh, I'm thinking the vector is right here. And then it does an unencoding, which means, oh, I'm going to move from vector to token. And it tells you what the token is. Matter of fact, what its job is it produces a probability distribution over all tokens. All the tokens. Remember, we have you might have 60,000 tokens. As a matter of fact, Llama 3 has a lot more tokens. It has 128,000 tokens. These are ways to break down words, or that may be words, but it has 128,000 of those. So it finds the position of that final vector, that's going to be the word, but it has to figure out what's closest by. And if you're really close by, so let's say here's what you had. This was the final, your guess about where that final vector is. Deck is here. Deck is close. Board is here. So you're a little bit farther away from board. You're a little bit closer to deck, right? So you're going to make deck be like a 0.7 probability. Board is going to be like a 0.4. Cinema is like way over here. That is nowhere close, right? So you're going to give 0.7 to deck, 0.4 to board, and guess what? You got it wrong. Okay, so now what's going to happen, this is the learning part, through backpropagation, it's going to go through and modify the weights of modify all the parameters so that the next time it'll get closer to board, it'll move away from deck in a useful way. It's like, no, this vector needs to move away from that. I'm going to try to move it in a different way. I need to change all the weights, which gave me that vector in that position. So that's the learning, okay? And it's going to be, hopefully the next time that you run, it's going to be closer to board than to deck. So there's always forward inference, but then there's a very complex back propagation, which is much more computationally intensive. So inference, when you're running GPT-4, it's only running forward. When you do expensive training, which we're going to be talking about, that's a special use of this, and that's when we do back propagation. Most of the time when you're running this, it is never doing learning. You're never changing the weights. What's happening is the activations are changing because it's inferencing, but that's all the feed forward stuff. Does that answer your question? I'll take that as a yes. Sophia, you had a question first, and then Amir, I'll get to your question. Is unencoding different from decoding? Yeah, decoding refers to the entire, we overuse the term decoding. We use decoder, meaning this entire thing, this entire solution that you're seeing right here is a decoder network, but it's kind of it's a bad word for it, really, but that's just what I called at the very beginning. Unencoding refers to, you have a vector in a particular place, tell me what token is closest to it so I can move from embeddings back into tokens, back into text. Sophia, does that answer your question? I'll take that as a yes. Amir.
Yeah, so as you're chatting with ChatGPT in an interactive way, let's say it gives a response and you say, no, this is wrong, or this doesn't make sense.
Right.
Does it now update the, no? Okay.
So now your context has changed, right? So it knows you asked it for a thing. It told you a thing. That's all part of the text now. All of that just gets added, to ships at a distance have every man's wish on blank, right? That's been added. So now it's being added to that. So what is the proper response after? So what is the proper response given that you got asked a thing, you answered a thing, they said no?
Go with the alternative.
Exactly. Then the next token should be something else. Yeah.
So a single word no, which is my response, is now going to shift that vector so far that now the the most probable answer is not the original one, but the
Right.
second one.
Think about the influence that no has, right? That's going to influence everything around. And remember, it has a representation of language, so it's going to put the most of that no in the right place, right? But yeah, no, absolutely. That's what's moving it. It's not learning. It's simply responding to what you have said.
Yeah.
Does the decoder concept here go with encoder decoder? So keep in mind, what I'm saying is unencoding, which is a different thing. So when we talk about encoder network, an encoder transformer versus an encoder decoder transformer versus a decoder transformer, those are classifications types of transformers. Almost always with generative AI, we're talking about decoder networks, decoder transformers. Now, when we start talking about encoding and encoding and unencoding, I try to be careful to say unencoding. Now we're talking about the process within that transformer algorithm. It's a process, not a type. Mohsen.
Yeah, hi. I wanted to clarify. I think I understand something, but maybe some of the jargon is a little confusing. When you say activations, you're talking about the vector, right? That's the vector, and then
So,
you have weights. So like I think you mentioned that the weights don't change when Amir asked that question about when you say no, the weights don't change, but what's actually changing is the vector or you said something like the activation changes.
yeah, so be sure to, at the repo, be sure to follow that link to three brown, one blue.
Three blue, one brown, yeah.
3 blue, 1 brown, to actually see what's happening, because what I'm talking about is the deep learning network. So the deep learning network has weights. When you train a deep learning network, what you're doing is you're changing those weights. And so the same input now will have a different effect on the output. Activations has to do when you're actually multiplying things through and you're deciding whether something gets, activated or how strong something is activated. That has to do with with when you're multiplying forward. So go and watch that. I think you'll get a much better sense of that, because we're not really talking about that here too much, because otherwise it would. But definitely watch those videos. I think those are terrific. All right, let's go ahead and let's go forward. So we have our network here. We talked about the fact that it's through additional training that the model takes on new capabilities, that decoder-only models, these generative AI models, take on new capabilities. You don't have to have new architecture. You can train them to new things, and they can take on vastly new capabilities. So, Sophia, you had asked me about how, actually, do you remember what your original question was? It had something to do with how the models know. What was your original question? Do you remember? Sophia, you might have stepped away. All right, so
was it
go
the
ahead.
question about unencoding being different from decoding?
Yeah, you had the question about unencoding. At the very beginning, I thought you had another question.
I think that was my only question.
Okay, then I might have the name wrong. I'm sorry, Sophia. I asked somebody to remind me about the question that they asked at the very beginning.
I think it was Tara that asked that question.
Yes.
About the what was the leap that Databricks took to their new.
That's it. Okay, great. So let's talk about leaps in models. How would you make a model more knowledgeable about the world? What are some ideas that you have? How would you make a model more knowledgeable about the world?
Give it input, give it more
Okay.
examples, right?
Yeah, okay, yeah, so you can do that. You could give it more examples, like in the context, right? Absolutely. Is there another way that you could give it more examples, or do you mean in the context, or do you mean training, Tara?
I guess probably I mean training. I'm thinking of unsupervised learning where it.
Right.
Yeah.
Oh, that's great. Yeah, so you can train it, but let's say that the model has a limit, right? And the model has a limit to how much it can know. because it only has so much space to represent things. And even though it's not a database, it's still, there are limits to what it can represent. What is one way to increase what the model can represent?
Like categorizing based on different contexts, like when you have chunking of, I don't know if that concept.
Well, you're right. That's what we do, especially for working memory. But for these models, what part of the model could you expand? And Tara, I think you were about to say, yeah, suggest one.
Is it the attention that you could expand?
So attention is cross communication between tokens.
Gotcha. So it's the
Um,
tokens you could
Well,
increase.
actually, that's interesting. That is one way to sort of be able to represent more. But how about just learning? And I can go back here to our blowout here. What part of this was responsible for adding information to each individual embedding? Right. So remember, I said I had cat over here, but it was informed and moved by Het and 50s poet. But in order to be informed, so what part of the network was doing that? Was actually, so it's already been informed. Now I'm going to enrich this meaning by putting some additional information like, hey, this is a person, not a kitty, and they might wear a beret.
Is it the positional embeds then?
No, because that's it's got to be in this encoder block. Let's restrict our attention to the encoder block.
Oh.
Yeah. And
is it so if it's not the attention, it would have to be the feed forward.
Feed forward. So what happens in a feed forward network is it re-represents what you put into it. It enriches it. So now this is cat, but now this is a person. This has the meaning of person and a particular kind of a person. All that is feed forward. The world knowledge is in the feed forward network. That's where all the knowledge of the world is. So if you only have this much space in the feed forward networks, one way to make the networks better is to make that feed forward network bigger, bigger, and bigger. So the big difference between these models that are, a couple of billion parameters and the ones that are like 500 billion parameters or a trillion parameters, almost all of those additional parameters are coming from the feed forward network. So you're either getting more decoder stacks, or you are getting bigger stacks, and probably both. More of the decoder stacks, which is both attention and feed forward, and also the feed forward part of that being grown. So that's what's happening when you get to these very large networks. They get large so they can represent more, know more, and take on more training. So that's what happens here. One way to make the model better is to make that decoder stack, more of them and bigger. So now the other challenge is we know that and also there was a suggestion of more dimensions in the embedding. Actually, yeah, that can help too. That allows for more richer representations as well. But for pure knowledge, you're going to want to increase that the feed forward network. So here's another way to increase and to improve models is the context length, because we talked about how important it is to give enough context for the model to be able to do well. So another way to do that is to increase the context length. And we've recently had so we started out at like 8,000 tokens was big. And 8,000 is like 6,000 words. So a couple of typewritten pages and then you're out of space, you had to start over. Then we got up to 32K. That's much better. It means you can go on longer. You might even be able to put some more reference material right there in the context. 128,000 tokens, fantastic. Now you can put a couple of papers in there. And when it's answering questions, it doesn't have to depend just on what happens to be in the decoder stack. It can actually go into what you've given it before. So here's 2 whole papers that are about this topic that I'm going to ask you about. Using attention rather than just retrieving, using attention, answer my question. and it can use attention to go and really inform what the answer is. It could actually just pull it out. You asked about the author of this paper. Well, that's over right here. So I can tell you what that is, and I can get that exactly right because it's all in my attention. It's all in my context. And now, available now, Gemini 1.5, 1 million tokens. You can put an entire book in there. So once you're at this level now, through attention alone, you don't have to depend on that decoder stack, those feed-forward networks to roughly or approximately represent things. If you want to use something, you can put it into that context. Amir.
What if in a book, in different chapters, the same word could have different meanings, like the 2 cat examples that you're talking about? And so if it's given that input, then, and it's calculating the relationship, how does it know which cat you're, like
from the context. So I mean,
local, does it also look at the local words?
Exactly. So as it goes through each of, remember, because each of those embeddings, it knows about it. It knows about position. And also one of the secret sauce of getting to 1 million is that you also encode that position encoding in a different way. So it makes it more useful. So that was a key part of increasing these attention, this context length. So absolutely. So let's talk now about how you can use context to solve other problems here. So let's say that I'm going to ask the model, when was Vanderbilt founded? Question mark. So if I were to ask a GPT this, it's going to have to actually hopefully have this encoded somewhere in here. And then it might be able to answer here, might, right? Was it trained on when Vanderbilt was formed? Yeah, maybe, maybe not. So how can we do better? Well, remember, I should have erased that. I'm gonna have to rewrite that now. Oh, well. So we have the question, when was Vanderbilt formed? When was Vanderbilt founded? Okay, question mark. So one way to solve this is you give the model the ability to look things up on the internet. So the model could be trained using instruction fine-tuning. So you first do the base model training, and then you do the instruction fine-tuning. And with the instruction fine-tuning, you train it so that if it gets asked factual questions, that it will generate, what it first generates is a Google query. So it could be, and actually, the first ones were Bing for GPT-4. So, Bing question, so it can do a Bing query, a Google lookup, and then it just, when was. So then what it does is it sends us out to Bing in the case, but it was Google before. And then what it does is it takes the answer and puts it right in here. Vanderbilt was founded in, oh God, it's 151 years ago. Somebody do the math for me. What is 2024 minus 151? And please don't tell the chancellor that I didn't know this off the top of my head. Can somebody put that? What is
1873?
1873? Thank you. Fantastic. So Vanderbilt was founded in 1873. When was Vanderbilt founded? Well, now the model knows how to respond. Why? Because it was put into the context, the answer to the query. So now it has, when was Vanderbilt founded? Vanderbilt was founded in 1873. What's the response? Remember, it's a chatbot. And it might say, sure. Vanderbilt was founded in 1873, and then might even add other information. So what's happening here, it's doing two passes, right? One, you ask a question, it realizes it doesn't have to have the answer, and so it does a query. It writes a query, takes the answer to the query, and puts it back into the context. This trick of looking stuff up and putting it back into the context is the core of many of the tools that we use today. So let's go ahead and change this around a little bit. If I wanted to say, hey, do this math, then it would write and call a calculator and say, what is 356 times 24? And then it would put that back into the context, and then it would answer you. Because now in the context, it has your original question plus the answer that it found using a tool. So does this make sense? The tool used by GPT models. Great. Now let's talk about RAG. RAG is a little bit different. Okay. So let's say, and I'm gonna do RAG now. Anybody remember what RAG stands for?
Retrieval augmented generation.
That's right. And what do we mean by retrieval augmented? It means we're getting something from over here somehow, and we're putting it in here. So that's what we mean by retrieval augmented generation. It's augmented in that it's been added to the context. Let's talk about how that happens with RAG. With RAG, it's a little bit different. So RAG assumes that you already have preferred documents out here. So these are the documents that you want to use to guide what's happening with the answering of questions. And actually, these documents are chunked based on their size. So they're chunked up because you don't want, you'll see why in just one moment. So what happens is, when was Vanderbilt founded? If I'm using RAG, it will first do a similarity search against these. And it will say, oh, this was somewhat similar. This talked about Vanderbilt, but it was really talking about the majors in Vanderbilt. Boy, this chunk is perfect. This chunk talks all about the history of Vanderbilt. So this chunk is going to come back. I'm going to pull it back in here. And this chunk is going to be brought into the context, just that chunk, not the whole document, just the chunk. But that chunk now is relevant and actually Vanderbilt was founded in 1873 with a generous gift by a man who had never actually visited the place, you know? So it has all that, and it has it in the context, and then it can do the same thing of saying, sure, and then give you the answer. So retrieval augmented generation first does a similarity match. So it does similarity, and then does a retrieval of a chunk. Okay, but everything rests on things coming back into context. All right. I didn't ask anybody to make breakout rooms. Did anyone on the DSI team make breakout rooms? Don't see breakout rooms? Okay. Then let's see if we could make breakout rooms. Let's see. Abby, could you make breakout rooms again? Or Sharo, had you already started on it? Okay. Abby, could you make breakout rooms? Let's do the following. We haven't had a break yet. So I'm going to ask you to think about something, and then we're going to take a quick break. We're going to talk about it again, and then we're going to do breakout rooms. So let's take a 10-minute break now because we've gone strong, going straight. My question that I'm going to ask you in the breakout room is this. So be ready to discuss this. Does RAG solve the problem of hallucinations? So first thing I'm going to ask when we come back from break is for someone to tell me what I mean by hallucinations. And by the way, I'm going to tell you, I hate the term, and I'll tell you why. But let's go and take a 10-minute break. And when we come back, Abby, would you be able to create the, I'm taking away, okay, would you be able to do that? Okay, great. Then in 10 minutes, we're going to come back. I'm going to ask you what hallucinations are, and then we're going to go in breakout rooms and discuss whether RAG eliminates hallucinations. All right, so it's going to take 10 minutes. I'll see you back here at 10:30.
And Jesse, can you just make me a co-host?
Oh, you're not a co-host? Oh my gosh. Okay. Yes,
Awesome.
you're co-host. Thank you so much, Abby.
Yeah.
All right, folks, time's almost up. We're going to be starting up again in just 30 seconds. All right, welcome back, everybody. All right, so first question, what do we mean when we say hallucination with respect to large language models? Michelle.
So that's like when it produces like an output that's like misleading or like nonsensical.
Right, right. That's exactly right. So I mentioned that I didn't like the term. And the reason why I don't like the term is that we pretend like all of a sudden the model is doing something unintended. The only term that's worse than hallucinating is lying. The model is lying. Why is the model lying? But we were just talking about what the model does. The generative AI models, decoder models, produce a probability distribution over the next tokens. So here is my vector. Here are the here are the nearby things. I'm going to give you a probability distribution. It is a 0.7 probability that the next token is DEC. There's a 0.4 probability that the next token is bored. Well, if you give it a crummy context, or you ask it for something it doesn't know and it doesn't have tool use, it is going to continue to produce next most likely tokens. The funniest case of this is the lawyer that used an early version of ChatGPT, which does not have tool use, right? At the time, did not have tool use. And so it generated, he was asking it for cases, law cases, right? Court cases. And it generated court cases that were realistic sounding. It didn't know about the court cases. It only had so much knowledge, and was it well trained on that particular case law and those particular examples? No, but it knew how to format them. It knew that the person was looking for criminal court cases of a particular type, and so generated plausible responses, because we've trained it to produce tokens. So of course, actually took this to court, and you're like, oh my gosh, the model was hallucinating. It didn't do what it was supposed to do. Well, no, the model did exactly what it was supposed to do. We were thinking about it incorrectly. So we call it hallucination when the model produces something which is not factually correct. So here's the question, and I'm going to ask you to go out into breakout rooms. And Michelle, that's a great question. It's all about the prompt. Could be, right? So let's say that we have RAG now. So RAG, you ask about a court case, and maybe all of these things over, on the right, those are court cases, right? And so it's able to pull out specific references to court cases. So let's go into breakout rooms, and let's go ahead and do this kind of quickly. We'll just do 5 minutes for the breakout rooms. Is that okay, Abby? 5 minutes with a 60-second warning. Does using RAG, where we modify our input context based on some, retrieval from documents, solve hallucinations? And we'll go out and we'll see you in about 5 minutes. And Charo, would you be able to handle questions? The office hours. Larson just got out, so after today is Larson's surgery, so and they just got out, so I'm gonna head over there after we finish up. Okay, thank you.
No problem.
Did you all see the OpenAI exec saying that GPT-5 is going to make current models look like nothing compared?
Yeah. And my favorite quote was that he was embarrassed by GPT-4.
I too am embarrassed by it. It does so many things wrong for me right now. How is it that they become worse over time? I still don't understand that. Is it just poor training?
Yeah, I think that catastrophic forgetting doesn't have to be like catastrophic. It can be like you just blow holes. Yeah. Welcome back, Katerina.
Like save
Thank you.
states of these models somewhere.
Hello, Kevin. Hello, Yi. Welcome back, everybody. Rooms will be closing in about 15 seconds. We'll have everyone back in then. And I forgot to remind you all about the link to the rooms document, but that's fine. Here comes everybody. Welcome back, everybody. All right, so we're still filtering back in. Let me go ahead. I'm going to just call on some folks. Tom Martin. Tom, what are your thoughts? What do you think? Does RAG solve the problem of hallucinations?
It can't solve the problem of hallucinations because that's intrinsic to the statistical probability engine that lies behind LLMs.
We got right to it. Yep. So they're always going to be producing probabilities. So it can make it more probable. I'm going to wait for other folks to get in here. And Tom, I'm going to ask you to repeat that too, if I could, as the rest of people came in, because it just nail on the head. Welcome back, everybody. Tom, I just asked you, does RAG solve the problem of hallucinations? And what did you just share?
I said the short answer is that it cannot solve hallucinations because it's a result of the statistic probability engine that lies at the heart of LLMs. Yeah.
So what can happen is that by providing better context, then you ameliorate, right? You mitigate. Because if let's say that I say, what year was Vanderbilt founded? And now I've augmented that with something where it's a document where it says Vanderbilt founded in 1873, and that's the chunk that it has in there. Given all of that, what is more likely, 1873 or 2001? It's like, 1873 becomes much more probable because it is actually in that context of what you have. So here's a question. Here's an answer to the question. What is a likely response? The answer to the question. But it's not an absolute. None of this is going to be an absolute. Some of you in your write-ups, and I love this, I forgot to remind you of the write-up page, also pointed out that there's sort of an extra step in there with RAG, right? Which is you've got to match the similarity to the documents first, and that's not going through the LLM. That's actually just doing a direct match of whatever you happen to have written against the embeddings of against the documents. And remember, they're chunked, and so they could be chunked in the middle. If you're really, really bad at chunking, then you could have Vanderbilt was founded in 18. And then the next chunk says 73 by a man who, nothing keeping that from happening. So RAG doesn't solve the problem. With proper chunking and a good retriever, it can mitigate. So think about this. What would be, so that's other comments about RAG, and other thoughts about RAG? Yes, Amir.
We had a conversation about a prompt that when you ask ChatGPT a certain question, then you can ask it how much of it is factual and how much of it is not, or rate yourself. Tell me how much of it is factual. And it does a good job usually. It tells you what is opinion and what is not. And I wonder, does it have to do with the amount of information it have tagged a similarity to the existing documents out there? Is that, like, does ChatGPT do this too, or?
Yep, it is all now keep in mind there's a lot in probability distributions, right? Distributions are information. But it is not, doesn't have a separate tool, right? That it's calling to do that kind of work. Now it can do complex, and we'll talk later on about some really amazing things that it can do, but really it is all based on the exact architecture that you've just seen, right? The attention and the feed forward in layers, right? And so can you move that around? Is it moved around when you say probability? It's going to give you an answer. It might be moved by additional knowledge, but really that is all that is happening unless you're augmenting it with some other tool.
Okay.
Yeah. Fantastic. All right. So let me ask you this. Given RAG that you're looking at right here, can I ask the model to synthesize all the information across all the documents on the right? Let's say I don't chunk them. Let's say I just have them all right there. Can I say, summarize these 8 documents? RAG can't quite do that, right? RAG is trying to take what you asked and match it against the contents of the documents, against chunks of the contents of the documents. It's not working with the documents or across the documents. RAG is in a process that takes place outside of the LLM, pulling back specific parts of documents. Where would these documents have to be in order for me to answer the question, summarize the similarities and dissimilarities across all the documents? Where would the documents have to be in order for an LLM to be able to do that?
In the context.
That's the only place where it knows about these things, right? So let's go ahead and we're going to move them here. We're not going to do RAG anymore. We're going to get rid of all this stuff. We're not doing RAG. Now what we're doing, and we're able to do this because we have a honking long context, is we put these documents actually in the context. Oh, I had too many. I only had 8. All right, so they're all in the context. So, a couple of things here. One, when we did have these over here, the nice thing was that you could have RAG do a special thing to tell you which document it pulled the information from, right? Here, though, it's able to synthesize information across and within all of the documents. You might be able to give it information on the surrounding text or things like that, but it's not going to be able to cite where it got something from as it did here. But think about this. Now you can ask holistic questions. So long context models do some of the things that you might want to do with RAG. Maybe what you want to do is both, because you can imagine RAG here, right? Where what it's doing is it's not chunking anymore. It's pulling the entire document over here. So both and can be a powerful way to work. And this is a recent advancement in models that they have these long contexts. And we're going to begin to see new types of use cases where you do things like this, where you pull everything into the context so you can reason against the entire thing. I'll give you an example of something that we did fairly early on. When Claude first came out, we were interested in, and this is with Joshua Su, who you're going to be hearing about from in week 2, I think. And he was interested in starting work on modeling the action of water in protein-protein binding. So it turns out in protein-protein binding, a lot of the work that was done was just, assuming, no water is just sort of happening. Okay, yeah, so it binds here, great. So that means this particular drug you're coming up is going to have this particular action. So he wanted to start thinking through all of the issues. So he uploaded all the papers having to do with relevant papers having to do with protein-protein binding, with the code base for the current, for the code that was developed to do this, called diffdoc. The entire code base. So, this would be, this would be an article on, on protein-protein binding. This one might be the entire code base, all the computer code having to do with that, and then other documents as well. And was able to have a conversation. Okay, so I want to account for the action of water. How must the code change? What if this is true, but this is not? What are some alternative approaches? And was able to reason, we were able to reason against all of those together and actually generate code which was consistent with diffdoc, but updated and new. And so that's something that we've never had the capability to do before. And we're able to do that because we're not using RAG. It's all in context. So I put this forward to you. As you're learning this very material, we're going to give you articles to work with, and my ask of you is to use long context models in this way, to ask and answer questions, to synthesize information. Think about your own research or your own classes. Imagine being able to put multiple book chapters together and asking to synthesize that information. If you're programming, think about putting the entire code base in there, and you can say, I want to write a function which does this. Can I compose this out of existing objects or functions? Here's a thing that I want to do. Is it already done somewhere else in the code base? Extraordinarily powerful. All right, and let's see. And you have your hand up, and it's a Mohsen.
Yeah, thanks, Jesse. You brought up the issue that about how RAG can't do text summarization, or it's hard to get it to do text summarization. But so I'm trying to reconcile that with what I think I do with ChatGPT 4, where I have created my own GPT, and you can upload your own files.
Mm-hmm.
So I'll upload like a research article, or I'll upload code, my own code, and then I'll say,
and just quickly, you're uploading it sort of over here, right? That's what I
thought we were doing. But that's what I thought we were doing. But then I'll ask it, can you summarize this, or can you create an outline for this of this article?
Yep.
And
so
then
it
does it. It seems like okay.
It's good. What it would be doing then is pulling in chunk after chunk after chunk. Is it pulling out all the chunks? Maybe. But you're dependent on the RAG algorithm doing that for you. And the question is there enough context length to bring it in? So what's happening behind the scenes is that parts of that are being brought into your context.
Oh, okay.
Right. And is it all being brought in? Do you have enough context length to bring it all in?
So to that point, is the issue, obviously it's the issue of do you have enough context length, but then you mentioned something about a RAG algorithm.
That's right.
Are there different RAG algorithms, I assume then?
Oh my God, right. Because actually what's happening is, and so here, this is, you can see, you're going to start getting the sense that embeddings are at the heart of everything. So it takes a document here. Man, I cannot draw to save my life. There we go. There's a document. And it breaks it up into chunks. What size are the chunks?
That's part of the algorithm.
Yeah. If you're going with OpenAI GPT, it decides, right? But it does the chunks. And what it does is, for each of these chunks, it calculates an embedding. So it does an embedding here, just like we've been talking about. So it has an embedding model, which may be the same model that you're using, could be, you know, or it could be another model, but it's coming up with a vector representation of that chunk. And then it's comparing the vector representation of your context, which is also another vector. And it says, oh, here's your query. Here's the chunk. Here's another chunk. So I'm going to call this chunk in, but I'm not going to call this chunk in. So it's doing a similarity based on the embeddings to figure out which ones to bring in. So here are the questions to ask, which you may or may not know the answer to. 1, how long are the chunks? 2, are the chunks done in a reasonable way where it does not break across information that you need? 3, is the embedding algorithm, the chunking algorithm that's used, appropriate for the documents that you have? Does it know enough about the content and so it could come up with a good embedding? 4, are you pulling in all the chunks or one chunk? 5, if you're pulling in multiple chunks, how do you decide what's going in? 6, what's your context length? You can pull it in. All of these are unknowns. We're going to find out a little bit later on in the class. I think we're going to be talking a little bit about how to build. Actually, Shara, do you remember, are we talking about how to build RAG this summer? We are, okay. So we'll actually be talking about how to use a framework called LangChain to do this. But now you have another choice. You could either use RAG, or you can pull things directly into context, or you might into a very long context, or you could do both. Lily, you had a question.
Yeah, I'm a little bit concerned about the security. Are you gonna talk about it throughout the course, or at any certain point during the course?
Absolutely.
Okay.
I don't remember
Awesome.
which week it is now.
Uh,
I think it's week 3.
I have, like, for example, the Amplify, the Vanderbilt AI.
Yep.
Is that
We're going to be talking about that
possible
next week. That's right. So a couple of ways of doing having things secure. One way of doing security is that all of this is in some kind of a secure environment. One secure environment that we have, and we're going to be talking about this next week, is Vanderbilt AI. So this is either going to be level 2. I don't know if we're to level 3 security yet, but this is all working within Microsoft Azure. And it's a secure, it's a secure area of Microsoft Azure that all of this is running in. So behind the scenes, it does RAG for you. The entire model is running. And so level 2, and we're supposed to be getting up to level 3. I just don't know if we've gotten there yet. So still in the cloud, but still much more secure than just doing it to GPT-4 and you're giving all your data to OpenAI. Another way to do this is, go ahead.
I'm sorry, is it also using the rule-based security, or just using Azure? Like
so it's using Azure, and then it's in a dedicated Azure environment for Vanderbilt. So that's
for example,
sort of
if I upload a document or a database information, I want it only specific group of people to read this info. Is that possible?
It's
awesome. Okay, great.
Only a group of people that we're getting there. So it's being built out sort of as we speak. But yes, I think that we will absolutely get there. And this is Amplify. So Vanderbilt.ai is Amplify. And that's a secure way to do this. And it's being developed, so new capabilities and higher security will come as we develop. Another way to do this is, this does not allow you to share, but another way to do this is you could actually run this on your own machine. You have to use smaller models, but especially with Mac with M1, M2, M3, and the soon to be announced M4 was announced, but it was only for the iPads. But M4 will soon be on laptops. You can run this entirely locally if you want to have this perfectly secure. So you have different choices, but know that yes, when you're uploading information, it's going to be Maxwell, you're on the VOT security dream. Maxwell, thank you so much for bringing that up. What we're going to do is we'll be mentioning this and sort of steering people out to what security actually, what it looks like. Thanks so much, and thank you for your work on this, Maxwell. All right, there were a couple of other questions. Let me go and answer those before we run out of time. Who else had a question? You had your hand up. Esra.
So
you just listed approximately 6 questions that come about when using RAG. Can we mitigate those by having more specific prompts to draw upon the entire body of knowledge?
So that key of drawing on the entire body of knowledge, you mean body of knowledge here? Or do you mean body of knowledge
in the top right?
So body of knowledge here.
Within the
Okay.
context.
So there are, yes, so you can do things. And so this query over here works better. You can do that by tuning the model that's doing the embeddings. That's one way. And so it does a better match. It knows more about the content of these. It knows more about that subject area. So that's one way. So it does a better job of matching. But when you talk about body of knowledge, that's if you want to do it against the entire body of knowledge rather than pulling out parts to reason against, that's when you need the long context. You're not going to be sure if you're getting everything unless it's in context. Because really with RAG, the whole point is get the right things into context. And if you're asking about reasoning against the full body of knowledge, the right things are all of it. So really the appropriate thing is to move that all of it into context if you have those type of holistic questions against all of the knowledge.
Thank you.
Absolutely. Other questions? Yes, Michelle.
So as far as using like a long context model, is this when like you would want to put it with maybe like something that's like like the dual chunk attention? So if you're for your agents to be able to multitask, is this when you would be putting things together so then they can communicate? Like, is that?
You could, right? I mean, you can easily imagine where you have one of your agents is a long context model and has all of the documentation uploaded, right? Is like in the expert in answering questions about procedures, right? And then another one, which would be responsible for solving a problem and would say, well, if it's appropriate with procedures, so procedure agent, is this appropriate? Great. Well, okay, now we're gonna have to write some code. Programming agent.
Okay, so then that's how like they would all be communicating well together.
Yes.
You're still performing like it's all for like one specific task, but it's they're each having their own job, so to speak.
Exactly.
Okay, cool. Thank you.
Yeah, absolutely. All right, folks, we are at the 11 o'clock hour Central Time. We're going to pause here for a moment. So some homework for you. You all have started to have conversations with ChatGPT about GPT models. I'm going to ask you to continue that. I'm going to ask you to go and try out a long context model, and you can get a few turns with Claude. If you're on Vanderbilt, you can get to Vanderbilt AI. It's a little bit tricky there to know whether you're getting the long context model or whether it's doing behind the scenes chunking and RAG. But I'd like for you to experiment with actually reasoning against a large collection of documents. It's a very powerful way to move your work forward to be able to do that. We'll be sending out some information. Remember, we're not going to be meeting on Friday. We're going to be picking this up again on next week. We'll be sending out an email just reminding you about it and about the topics we're going to be covering. We're going to be here. I'm going to be here for a few minutes. Other folks from DS Data Science Institute will be here for the full hour. But thank you all very much for your time. Congratulations. You've covered a lot of material today. So fantastic. All right. I will see you all on Monday. Feel free to stick around if you have questions for our office hours.